is for good morning, everyone. I welcome Professor Ramjee Prasad, sir, Dr. Devendra Singh Gurjar, sir, and everyone. So, the topic of my presentation is hybrid FSO RF systems for 6G. Uh, free space optics. Free space optics is also known as the optical wireless communication. In this, the visible light or the infrared light is used to transmit the data. It is for the short to the medium point to point communication. The main primary principle for the FSO communication is it requires the line of sight path. Some of the advantages for the FSO communication is security, high data rate, immunity to the electromagnetic interference, unlicensed spectrum, low cost, and it is easy to install. But there are also many challenges in the FSO system, such as it is highly affected by the atmospheric turbulences. Attenuation, if there is any obstacle in between the transmitter or the receiver side, then it is unable to communicate. uh, Wavelength and the molecular absorption. As the FSO system is highly affected by the atmospheric conditions. So, the main wavelength range is for the FSO system is 700 to 1600 nanometer. From the table, we can see that the wavelength 690 and the 1550 has the lowest molecular absorption. So, among these two, 1550 is considered to be the best because it has the low absorption as well as it is safe for the human eye. Some of the applications based on the different wavelengths for the FSO system are like for the inter-satellite communication, it is 830 and the 1064 nm wavelength. So on for the deep space communication, it is 1064 and 1076 nm. Similarly, for the UAV to the ground link, it is 1550 nm. Radio frequency utilizes the electromagnetic waves in the radio frequency spectrum range for the data transmission. It has the high coverage and it is hardly affected by the obstacle in between the transmitter or the receiver end. Here from the figure, you can observe there are the different frequency ranges based application. Such as for the marine communication, the frequency ranges from 3 kilohertz to the 30 kilohertz. So on for we can see for the satellite communication, it is 3 gigahertz to 30 gigahertz and so on. So here is the small comparison between the FSO and the RF. When we see for the device sizes, FSO has the smaller device size as comparative to the RF, whereas the power consumption for the FSO is low and for RF it is moderate. FSO is highly affected by the environmental parameters, whereas the RF is affected by the interference multipath fading. Path loss is high for both of the links. Bandwidth is higher for FSO and lower for the RF signal, whereas the speed for the FSO is high and for the RF it is low. Security is higher in FSO communication and lower for the RF communication. Data rate is higher for FSO and lower for the RF signal. And EM interferences is there is no EM interference for the FSO system, but it is present in the RF system. So we have seen the both the advantages and disadvantages of the FSO and the RF communication. So we can consider a hybrid system which include both RF and FSO, considering their limitations. So these system helps us to mitigate the signal interference and the weather related disturbances. Also, it enhances the availability and the reliability under the severe weather condition. Here how these hybrid system works. If we are considering both the networks simultaneously, we can use both the networks for transmitting the data. Second one is we can access one of the best network among both of them. Third one is we use one link for forwarding the data and other one link for the return path. And most commonly we are using the fourth method, that is the top priority network, and keeping another one as the backup. Here are some advantages for the hybrid system. It enhances the reliability of the communication system, increase the security, data rate also increases, and reduce the latency, which are the key features for our upcoming 6G communication. But there are also the challenges, that is the synchronization, handover management, careful design, and the regular monitoring is required. So I have taken one of the example to showing how these hybrid systems are better while using alone RF or the FSO, and reference is also mentioned there. See, from the table, if we consider a snowfall weather condition, RF is available, whereas the FSO has 39.49% of availability. So if we are using the hybrid, we have the 100% of the communication. Same goes for the dense forest, where the FSO only dense fog, sorry, where FSO has only 0.51% of availability. And for the rainy situation, it is 14.29 for RF and 85.71% for FSO. So the hybrid communication has 85.71%. So when we are using this hybrid communication, there is a trade off between selecting the suitable frequencies for this hybrid setups. uh, Desired data rate and cost requirement would also play an important role for selecting which one may play the backup or which one can be our primary link. So the techniques which we can include in this hybrid system are adaptive link switching, RIS systems, machine learning based channel prediction. We can predict which link is useful, which link we can use at a time, or the optical wireless networks and the terahertz communication. Here are some of the applications of the hybrid system. It can be utilized in the V2N communication, ground to satellite communication, underwater communication, um, military scenarios, UAV based communication. So, the future research may include the adaptive link switching, quantum security, which is the feature of also the 6G communication, green communication, and the improved atmospheric models, that is using the better mathematical or the computational techniques to mitigating all these environmental factors. So the summary of the whole of the presentation is hybrid FSO-RF is a key enabler for reliable and the high-speed 6G networks. RIS, terahertz integration may also involve. Research is going on for enhancing the efficiency, security, and scalability. Thank you.
Issues with the FSO communication, like this atmospheric induced feeding can actually disturb the performance. So, what do you want to say about that?
There are various fading models we are getting to reduce this atmospheric turbulence reduced in the FSO communication. So we can able to decrease it also.
Any more question? Five questions. There's only one question. Four more questions. Somebody has asked four questions. So, question.
So you have mentioned some challenges also. So like one of the challenge was handing over when you're using hybrid. So how you hand over, like what are the problems in handing over from one network to the another one? Yeah.
There are the two links. One is the RF and one is the. We are trying to use the switching methods like hard switching or the soft switching, but still sometimes transition from the RF to the FSO we get the problem. But we are dealing with it and most of the techniques are coming for this. But currently we are using the hard switching and the soft switching for this.
Hard switching means like sudden switching sort of.
It's mainly based on the signal quality or the SNR ratio. And the soft switching is which we transmit the data from both the links according to the communication requirement.
Thank you.
Third question.
because you have said about the hybrid communication, one is five free space optics that probably worked on around 300 or sub 300 gigahertz band, and your RF probably will be little bit lesser. So if you have to work on a device that will be able to switch between these two communication, you need a very wider bandwidth. So how do you think that designing of those device, which will be working on say 60 gigahertz to switching from 300 gigahertz, probably something like that, I can understand. Like you are using 60 gigahertz millimeter wave communication probably, and then you are going for 300 gigahertz or beyond.
So when we have the we are using the FSO is the primary. So when
Okay, okay, answer that is, we have two systems, RF system and FSO system. We can design both transmitter and receiver as separate transmitter and receiver. So there is no problem like I think you were asking like to design a system which can transmit FR1 and FR2 band that will make the complexity better. But here in this case, everybody is talking about separate
separate
frequencies.
transmitters.
One is FSO which will be having different set of equipment and one is RF. So switching is required when we use one and we keep one and two.
Last question.
In case of rain, I guess the efficiency was 84, 85%. Is there any way of integrating some other technology to get 100% efficiency or something like that? Because 84% is, I think, is less, because in 6G we are talking about ultra reliable. So it has to be above 98, 99. So how can we mitigate that?
We are working on it. That's why it's a future pieces.
Okay, thank you.
We will get more and more.
Any question? Nobody. Thank you very much. Thanks for bringing us this short meeting. Very good for life.
Hello, hello, hello. Am I audible? Hello.
You are PhD student.
Yes.
Neha is also PhD student.
Yes. Sir. So they all are my juniors. Neha and Partha are my juniors.
So your presentation could be better.
Much better. Much better. And who is the professor? He.
Even good. Good.
He should also, at the end, he should give a presentation. That should be the best.
So first of all, I would like to welcome Professor Ramjee sir to be like to make ourselves like very proud to be in his guidance. Then I would like to like thank the professors, and I would like to start my presentation on intelligent reflecting surface aided wireless network, which is actually emerging techniques for the beyond 5G communications. And first of all, I would like to start with the era of the 5G, which was actually released by the 3G PP, the third generation partnership program, in in June 2018, which was released under in July 16, 2020, and the reference for that is given below. You can access the link, and you can go through the more details for that. And there, there several techniques were evolved, such as the machine type communications, then ultra reliable low latency communications, and then with the EMBB enhanced mobile broadband communication. Then for implementing these techniques, several emerging of 5G paradigms, such as the massive MIMO, then NOMA technique, then OBM, all were integrated to form uh, and to form these to integrate themselves and to move towards the vision of the for 5G wireless communications, which can offer the following applications, such as the multisensory augmented reality applications, which are applicable in the medical sciences, then for the gaming, then connected robotics and automation systems. Similarly, for this the several driving tech the trends are the reliability itself. Then it should offer a spectral efficiency. Then it should also offer the connectivity, massive connectivity to various IoT devices, which are actually located in a diverse and vast locations. Then and also they have to be integrated with each other, and they could offer the efficient communication with the users. And the various enabling techniques for the 6G communications are actually the they can be the mobile edge computing, which offers the computing at the edge itself. Then the massive machine type communications, which integrates the larger number of and vast number of the machine type the IoT devices. Then the very sensory nodes, and for them however, implementing these techniques offer the basic challenges, which is the channel itself, which is the propagating medium for the wireless communications. If we talk about, so this propagating medium, it actually it actually be it is the channel between the transmitter and the receiver. And it actually goes through a lot of fading problems, such as the path loss, shadowing, and this can be shown in the figure itself. To what are the possible solutions for them? So the three basic problems are that key. First, implement more number of base stations, which are actually sometimes not feasible in locations, especially in the remote locations, like such as the different terrains or mountains, or oil rig applications, where the base stations cannot be implemented, and that has to be deployed in some distant locations. So for them, we can employ the conventional relays. Even we can have the unmanned aerial vehicles, and that can be utilized as the relaying for the relaying operations. But however, they also have some drawback for the related to the energy constraints, then and the latency. And usually they operate under two different protocols. One is the amplify and forward and decode and forward. So the problem with the amplify and forward protocols for the relay is that they actually amplify the noise itself, so that reduces the signal to noise ratio and degrades the performance. And the other is the decode and forward protocol of the UAVs, which actually requires the complex circuitry on the UAV itself, which actually makes the UAVs more bulky, and which requires higher battery powers to power them, which again limits their operational time or the flight duration. Then the next is the new building materials, which are again, it's very difficult to break the whole world and build it with the new material. So that's also not very much feasible, or not a right direction for. So in this direction, the intelligent reconfigurable surface has been become a prominent contender for this future generation wireless communications. And so what are these IRS? They're made of different patches, which are just the sensory elements, and these are actually made from different PIN diodes, which offers different capacitor values, which changes the capacitances, and they can tune themselves in order to change their directions of the signal, the propagated signal, as shown in the figure here. A single as shown in the figure, here we have the n number of elements, where one element is shown in here, which can be made from which actually operates as a diode, which is made from the PIN diode. And then it is having most configure, we actually prefer that it is a passive it's a passive device. However, the research has been going on for the active devices also. But since we are moving towards an energy efficient and less power consuming device. So the passive nature of this has been more preferred over the active devices. However, the passive nature of these elements also imposes several drawbacks, which we will discuss in the later slides. So here, as we can see, there is a transmitter which needs to communicate with the two of the users, the user one and the user two. And so here, this RIS can be utilized as a reconfigurable channel, and it can go through the analog beamforming, and by using this analog beamforming, what it can do, it can beamform the signal to either user two or user one itself. And this beamforming can be also like in two different it can be also in two different ways. One, if for an intended, if user one is your intended user, whereas user two, it can be your unintended user, or it is a node which haven't got a token key, so it can act as a passive eavesdropper also. It can consider it as a passive eavesdropper also. So we have to, this RIS can configure itself so that it can nullify the signal, and it avoids any signal to move towards our user two. So it can also be a possible application of this RIS. Then from the previous slide itself, we can go through this, where there is a transmitter is communicating with the receiver with the help of the RIS having the n elements, and in the below it shows the matrix where there is a direct link from a transmitter to the receiver, which actually shows, and that the channel which shows with the channel of H D PBT, which is shown here there, and whereas from the different elements, like from the X is the channel is the transmitted signal from the transmitter, and it is, and this is the channel matrix for the from the transmitter to the element of the RES, where this is the channel from the receiver from the RES to the receiver, whereas this is your so from element 2, from element n. This denotes that the reflection matrices of the RIS, which actually can be configured for the RIS, and actually that can be optimized for our improvement of our performance. Then to illustrate the operation, a simple scenario of an IRS assisted wireless network is shown in the figure, where we can see that the base station is having m number of antennas, and we have the IRS with n elements, and there are k users which are to be assisted by the base station, and there is the link between the base station and the user is actually very shadowed or is very faded. So as already told here, from this element 1, element 2, element n in the center, they can be controlled by the reflection coefficients, which are actually shown by phi. So phi is actually an n cross n matrix, and this phi k is actually denoted by a diagonal matrix, which is shown below. So the received signal from the IRS to the kth user is given by equation 1, where we can see that it is having two components. The first component is the direct link, where your base station is having a direct link with your user. That can be denoted by the direct link of the channel matrix, and this X is actually the composite transmits data symbol, which is this one, no? Yes. So this component is actually the direct link, and here we can see this X. What is this X? So this X is actually the composite transmit data symbol, which is expressed as equation number 2, which is the summation form of the signal SK, which is SK is the unit symbol transmitted from the base station, and this WK is the weight vector, which actually comes from the digital beamforming vector, and it can be derived from the basic concepts of the beamforming. You can go through that. Actually, it's a very interesting topic also. And then the second component, which is actually IRS aided link, which have the three which has three subcomponents. One is the link. This is the link from the base station to the user. Then this phi of h. This is actually your reflection coefficient, which can be controlled and can be optimized. Then this g of x is your again your x is your symbol and the g is your gain, and this nk is your noise which is actually additive or Gaussian noise. And one benefit of this RIS is that it removes once your signal is received at the element of at the nth element of your RIS, so it can eliminate that noise signal. So once it is retransmitting the signal to your receiver, your noise is completely eliminated. So that's one of the benefit of this RIS. And so in the equation number 3, similarly, we can obtain the received signal at the receiver, where again this component shows you this is your direct link and this is your indirect link, and based upon this yk is your received signal, and this received signal can be used to obtain your performance matrices, like for your if you are moving towards the reliability, so you can get the data rates, then bit error rate, and other performance matrices can be obtained by using these signals, received signal. So what are the different application scenarios for this? Actually, I have included some references where so the first from the Dr. Huang, he actually considers a simplistic scenario which we already discussed, where a base station needs to be transmitted with the multiple users, and in this scenario they haven't actually the direct link from the receiver from the base station to the user. Then in the second scenario, where they have this access point, which can be used as a D2D communications also, considered as a D2D communications, where this device actually utilizes an IRS to improve the coverage and the signal strength. Or however, already there is a direct, as we can see, there is a direct link between the access point and the user. Then the next application is it can be used to improve the physical layer security. So in the first scenario, Dr. Zhang actually he implemented an access point where there's a direct link from the access point and the eavesdropper and the user itself. So here the RIS can be used to nullify the signal, so that the signal which is transmitted through the IRS link, it actually counters or it actually nullifies the signal which is actually here transmitted from the access point to the eavesdropper. So this signal can be nullified, and the signal received at the user, it actually have the multiple copies of the received signal. Then in the second case, this is a simple case where the transmitter is not having a direct link with neither with the legitimate receiver and neither with the eavesdropper. So here the transmitter is actually using the IRS to make the communication link. So what are the different challenges in the IRS based systems, which actually offers the open research areas to you, and you can explore them? So first of all is the channel estimation. As I already discussed that here we are discussing about the passive IRS. So the channel estimation is actually very difficult. For them, we can have these active elements also. Like for example, if we have n number of elements, so some some of the m elements can be your active device that can be used for obtaining the estimations. And there are some other techniques also that you can go through in the literature. Then the second is the interference management. It actually occurs when there is a case of massive MIMO, where there are large number of antennas present at the base station, which needs to be transmitted with the m number of or k number of users. So there it can have a lot of interference or intercept interference also. So it needs to be managed before implementing the massive MIMO with the IRS. Then there is a hardware and power consumption. As I told you, if we are going towards an active RIS, so it needs to be we have to make sure that the power consumption is actually we have to move towards the efficient power consumption. Then scalability and deployment. Again, since we have having the number of elements and if we want to increase the number of users, so similarly the elements of the RIS needs to be increased, which actually again enhances your interference problems. So that has to be concatenated with each other. And the last one is the security, which I already discussed with you. So thank you and questions.
Question for the student. One question. We have question. Yes.
As far as I understand that IIS transmit the signal to the desired direction. Right? We are going for the full duplex mode, replacing the OFDM. So how it will work? Because once that we are transmitted to the current other direction, we have also received the signal to the desired direction. How is it going to work?
Actually, for that we also have an extended version of this RAS, which is termed as a star RAS. It is simultaneously transmitting and receiving antenna, like RAS. Where there we can have the your RAS. It can work under three different modes, like 300 different modes. One is your mode switching, then second is your time switching, the third one is your energy switching. So this mode switching can be utilized for this OFDM case, where it can be used for different modes for different uses.
Next question. Be bold. Last question. Show your courage. I want the courage for winning. Yesterday I had a meeting with a director. Director told me the students are very bright. Now show your brightness. Ask me question. Anyone, any student? They have to come forward. Ask one question. Receive a point.
How many maximum elements we can include in this IRS? What is the limit as the element increases the requirement of
Actually,
Meanwhile, I got in the Bangladesh student get ready to ask one question.
actually there is no some that such limitations on the number of elements. But again, as I told you, ki if we are moving as we are moving towards a massive MIMO, so for those massive MIMO we also require the large number of elements. And depending upon these application scenarios, these number of elements can also be configured. But actually, it has to be increased in the 2 to the power of n. That's a case.
Can we keep, say, finite number of elements? It should be 2 to the power n. Can we do that?
No, sir, that's not.
What are the problems?
Actually, you already like discussed some of the problems, such as your hardware and power consumption. If we increase the number of elements, so considering them as passive will be difficult, because if we as we increase the number of elements, so the power consumption will be also increased. And other thing is your interference also.
IERF is having passive components. Yeah?
Yes, sir.
So where the power consumption is like, be applicable.
Actually, the issue is that considering the passive introduces the challenges of channel estimation. So for that, the research works actually what they are doing. They are they are using some elements like if we have for example, if you have 64 elements in your RIS, what they are doing they are using 16 active components. So those 16 active elements are used to send the palette signals and all, and to get to estimate the channel.
So it is not having all components as such.
Yes, exactly, sir.
It is having some components.
Some components and pass active. Yeah.
Very good. Now the question from Bangladesh. Be bold and ask question. Any question, whatever comes to your head.
What is the security purpose of this IRF system?
Security purpose. See, again, if we are moving towards your massive connectivity, if we are providing a massive connectivity, so there is a difficulty in accessing the privacy keys, actually privacy tokens. So sometimes what happens your eavesdropper can be present near you, and even the legitimate nodes do not know that. This issue actually exists. There are two different types of eavesdroppers. Actually, if you know about you can go through the concepts of the security. Like this, eavesdroppers can be considered two different eavesdroppers. One is your active eavesdropper, and the second is a passive eavesdropper. The active eavesdroppers actually it sends what it does it actually like wiretaps, or it actually grabs some information, and then it sends that signal to one of its server. So, but what it have the problem with the passive eavesdropper is that it doesn't sense any signal. So it actually captures the signal, holds with itself. So that's a problem with the passive eavesdropper, and that's it's very difficult to to observe. Like it's very difficult to actually discriminate between the legitimate nodes and the passive.
Mention about like open nature of wireless
Yes, exactly, sir.
transmission.
Yeah. That's
The
also
transmitter is transmitting, anyone can receive it.
yeah, exactly.
If you don't have any security mechanism, you will not be able to like transmit information.
Information. Yeah.
Very good, Gaurav. Well done. Who is the third speaker?
So very well. So very warm welcome to regards to my everyone present here, to my professor, Professor Dr. Ramjee Prasad, and my teachers, professors, and my fellow colleagues who are present here today. Today, my topic for presentation is exploring the five senses of wireless communication. And if I speak about my background, uh, thank you, thank you. So I'm talking about my background. I'm from National Forensic Sciences University, and today my topic for presentation is exploring the five senses of wireless communication. And special thanks to Mr. Aditya Mohan Srivastav and Kartike Mishra for helping me to prepare the slides. Uh, no, I've prepared. I have also prepared the slides. They also have helped me in the research purposes. So. Uh, So I will start with the traditional wireless communication. Traditional wireless communication, we have sight and audio, which is there in the five senses of communication, which right now we have, which are discovered. So actually, the whole topic for the communication or the whole human bond communication, I took this from uh, research paper which I found it on the internet after I based it. The research paper was published by Professor Ramjee Prasad himself. So the whole presentation I took it from there, and human bond communication, which integrates five senses of communication. Huh? Yes, I took some help from that also. Yes. So I took the help of your research paper also. So the five senses of communication, here we can see the sight, hearing, smell, taste, and touch. So the as I mentioned, the human bond communication, here we can see that inducer distributed human bond sensorium and other factors which are here, which are necessary for olfactory, gustatory, and tactile interpreters, for which we can deduct and which we can sense for the audio and video uh, sense of recognition. So if I talk about digital and human experiences, so there are basically five senses of communication, maybe for eyes, ears, nose, smell, and touch. So which provides us an enhanced communication and helps us to provide an distributive network and for uh, basic understanding of communication which is going around us. totally around us. So there are basically two types of sensing modalities. One is one is wave based sensing, and another is particle based sensing. So what is wave based sensing? In wave based sensing, we basically talk about the wave nature, and with the help of wave nature, how we can communicate. So in wave based nature, we have optical and auditory. Optical and auditory, in the sense we can transfer or transmit the senses of communication with them using the electromagnetic waves. So as I can say that we can store them in case of any electromagnetic waves, and later on recognize them through the waves and distribute them in case of them. And another is the particle based sensing, which is right now in also another topic for research, which is right now not yet so much of researched as of right now. I research includes which includes smell, taste, and touch, requires molecular interaction. So it is a very bright topic to research, which the basic challenges for there is proximity, material replication, and accurate transmission. So the accurate transmission regarding the particle based sensing is very severe. So accurate transmission is not right now, it is not possible for particle based sensing. So smell, taste, and touch is right now for particle based sensing is not present. So in sensing modalities, we have wave based sensing and particle based sensing. In wave based sensing, we capture the sight and hearing and convert them to digital formats, and we can store them. But in particle based sensing, we include the smell, taste, and touch. So and the challenges we face there is proximity issues, material replication, and accurate transmission of difficulties. So there we are facing challenges, and here it is another major research topic for the particle based sensing. Here there can be many research which can be done. If anyone is interested, they can go for it. I start with the sight, which is the optic, which basic function starts with the color, brightness, contrast, and depth motion. So it is basically what we see, what we store, and how we can store what we see in that through communication. So human eye processes basically electromagnetic waves ranging from 400 nanometer to 700 nanometer range of. So retina, which contains photoreceptors, rods, and low light vision cones for detection. So these are the some topics for sight or optics. And optic nerves transmit signals to the brain for image interpretation. So for image interpretation for eyes, which you can see, so we can store them in image interpretation. So how the conversion technology works? So for conversion technology, we can use from basic lens and some CMOS cameras. So CMOS basically stands for converted mechanical. I currently forgot the CMOS program. So okay, cameras or an optical sensors convert light into digital images using CMOS and CCDs and lighter depth. So capture 3D. After capturing 3D, we have basically sir told us about AR and VR, augmented reality and virtual reality, how we can store them and how we can feel what we can see. So without being present at that topic, we can be feeling what is going on in the surroundings. And here how it works, sensor functions. The first of all, the photoelectric conversion is happening, and then the charge accumulation. The charge accumulation is done in the image sensor, and then it is transported to the ISP. There the transfer signal works, moves to the charge to detection node, and then the signal detection. For the analog to digital conversion, the ACD is used. So the ACD basic function is to convert the analog signal to digital signal and store it, and for the basic human preservation and image data conversion. And next we have is hearing, auditory, sound for wireless communication, which captures sound waves, and then we include speech, music, and environmental sounds which we can hear and store them. And with the use of basic wireless communication, we can uh, transport or transmit them to basic mechanism using the eardrum mechanism, which for human human range, which is 20 hertz to 20,000 kilohertz for human range, medication range. And if I talk about the basic mechanism of human ear, so the ear, what happens is when we the ear sound travels to the pinna, the basic opening in the ear, then it travels to the eardrum, and then it vibrates in the vibrates, creating some signals in the cochlea. So the cochlea hair cells convert the vibrations into electrical signals, which then are transmitted to the brain for further communication and for further understanding of the signals which are being transmitted to the brain. And then uh, we have conversion technology which is here. So how the conversion technology is there? So we can take the basic example of the microphone which is here in my hand, which captures the sound and converts it into electrical signals, and then everyone can hear it um, in the speakers itself. And then speech recognition and 3D spatial audio, and which helps in communication, emotional recognition, and other spatial awareness. So the role of HBC in auditory is that which enables voice recognition, spatial in VR, AR, and AI driven real time voice transmission, which is helps in natural speech recognition and voice synthesis. So here we can see how it works. Analog signal, first of all, is taken as the sample, and then captured sample data vibrates to the quantitype, and then the quantized sample data is then digitally stored using the digital signal, or here encoded using the where previously mentioned, the sound is transmitted into electrical signals, and then it is stored as the digital signal. So next, if I go, we have real world examples. Some, as I mentioned, the use of sound, immersive audio, and voice communication, spatial awareness in VR, AI transmission, and microphones, and eardrum, which I mentioned, biological mechanism which is present, and the smell. So the smell, which is basic, the thing of a human need, the role of scent in HBC, the human uh, based communication. The function of smell is that the chemical compounds which are present in the hair helps the perception of food danger and strongly linked to the memory. So once the smell is transmitted or smell is present inside someone, we cannot basically just store the smell. Right now we don't have the ability to store the smell as the olfactory nerves, but we can enhance it using VR and digital storytelling and telemedicine with scent cues. So which helps in remote training for chefs on perfumes and hazardous environment simulations. If we go into the mechanism, we can see that nasal receptors, which is present inside obviously the nose, bind to airborne molecules, sending signals to the olfactory bulb inside the brain. The olfactory system connects directly to the limbic system, affecting emotions and memories. So which is there in the diagram which is shown. Then if I move on to the smell olfactory real world examples, field VR masks simulates scents in VR environments and challenges. So if I talk about challenges, chemical sampling, digital scent encoding, electronic nose conversion for scent synthesizers, and NEC olfactory communication, developing digital scent transmission methods for smell olfactory in HBC. Taste. So taste or the gustatory digitalizing flavors. So the function of taste in a human is that we basically what we eat, can we store that, can we preserve, or can we tell anything what we ate last night? If I ate some dal, how the dal tastes. So if I want to tell someone the dal tastes bitter, the dal tastes sour, the dal tastes spicy, how I can communicate to him? So the how the tongue tastes, the tongue basically captures the taste of the functions are that it detects the sweet, sour, salty, bitter, and umami flavors through taste bud receptors, which is present basically in the tongue, which is there, which can be seen in the taste buds, and works with the olfactory system, enhance food perception mechanism, and tongue receptors interact with the food molecules, sending signals to the brain, and then thereafter sending signals to the brain about the taste of the food which we just consumed. And then the basic challenges in the technology of the olfactory system is that the molecular recreation and the precision of the taste transmission is basically very difficult to reproduce. So the need for universal taste and encoding standard is basically required in places like digital and audio, which is present already. So basically here, if I talk about the conversion technology of digital taste interfaces, here we can see that uses of electrical stimulation to mimic taste sensations and electrode based tongue sensors. So this was the small work which was done for in the University of Meiji, for real world example, which is also known as the Norimaki synthesizer, a device that tricks the tongue into perceiving different flavors. So basically what this device does is, if I taste something, the device will automatically convert the taste into something else. Maybe the bitterness will convert into the other sourness or anything else. And the taste buds technologies and challenges which I basically talked about is the molecular recreation, which is hard, and the universal taste encoding, which is not present, but which is present in audio and video, which is there. And the mechanism is basically the tongue receptors, and from the signals it sends to the brain. And the real world example which is present in the Meiji University, the Norimaki synthesizer, and the remote food tasting and functions which are there, which I mentioned right now. So next and most uh, fifth one is that the touch. So touch and tactile, the power of physical interaction. So the function detects the texture, pressure, and temperature and pain through skin receptors, essential for fine motors and object recognition and emotional bonding. So how the touch works. The mechanism is that through the mechanoreceptors detect the pressure and vibration. The thermoreceptors also for the temperature controlling and the understanding of the temperature, which is around the surrounding, sense of heat or maybe cold. And the nociceptors respond to pain or stimuli to the body. And the challenges to the technology, which may be the touch, tactile, the power of physical interaction. So basic challenges may be recreating the tactile sensations. So basically, if anyone touches me, how will I forward the communication, forward the basically my sense of humor, my sense of communication to him, that he touched me in the here, and he. So you need to understand how it touched me. So basically, if he touches you, you should understand that it is his finger and it is he himself. So how can you understand? So right now, the complex tactile sensation, grip force, textures, and resistance can be developed to provide some basic understanding of that touch. So need for high resolution haptic feedback for realistic interaction is mandatory for the touch sensation to be understood. Touch tactile continuation. Conversion in technology. Haptic feedbacks. Simulate touch using vibrations and pressure. Force feedback controllers provide resistance for a more realistic experience, or maybe soft robotic and e-skin, providing a lab environment for skin and mimic a human touch for a human using the AR, augmented or virtual reality. And the real world examples which may be present is provide realistic touch feedback in virtual reality and use ultrasonic sound waves to create touch sensations without physical contact, and a full body haptic suit for virtual reality applications. And so the HBC system components, human born sensorium components, are inducers which convert sensory inputs into electrical signals. And HBS, human born sensorium, manages secured sensory data processing. And HPT, human perceivable transposer, reconstructs sensory experiences using yeah, um, basic communication techniques.
easy. Pani. आराम से. Sit down. Easy. पानी की वजह से.